So we were talking about the Cholesky decomposition. And you can take, it only works for a symmetric positive definite matrix. It can be factored into a lower triangular matrix, and the lower triangular matrix is transposed, which is an upper triangular matrix. Okay, so this requires, you have a question?
Oh, no, I'm good.
So this requires approximately n cubed over 6 operations. Okay, so really with this, you only need to keep track of the diagonal matrices, diagonal elements. So here, okay, you only have to keep track of elements below the diagonal. That's what I meant to say. And if you can factor A into LL transpose, then you can solve any system AX equals B. Okay, so let's figure out how we define L. Okay, so here's the definition of L. Oh, you're gonna be doing this today, huh? Okay, it's gonna act up. Don't know why. Thank you. All right, so L. Oh. All right, so L is a lower triangular matrix. So we're going to do this for a 3 by 3, and then you can figure out the pattern for anything else. Okay, so it's going to be L11. This is a 0. This is a 0. L21, L22, 0, L31, L32, L33. Okay, so that's L, and then L transpose. It's going to take L, and it's going to be L11, L21, L31, 0, L22, L32, 0, 0, L33. Okay, and if you multiply those together, you get A. So A is A11, A12, A13, A21, A22, A23, A31, A32, A33. All right, so let's see. So when you go to multiply this matrix, the first thing that you're going to get when you take that first row times that first column, you're going to get L11 and everything else is 0. So you get L11 squared is equal to A11. So that then implies that L11 is equal to the square root of A11. Okay, so that's the start of it. Okay, so then we multiply the next, that first column by the next, by the row, and we get L11 times L11 times L21. and then everything else is 0, and that has to equal the A1, 2, wait a minute. L11, which way am I doing this? Oh, I'm doing this, okay, I did that wrong. It should be L21 times L11. So I'm doing this row times this column. Okay, so that's going to give you the A21 entry. So that implies that L21 is equal to L11 divided by A21. Okay, keep going. Next is we're going to take L11 times L31, and that's going to be A31. So that's going to imply that L31 is going to be uh-oh. Oh yeah, uh-oh. I think something's wrong. L21 should be A21 divided by L11. Okay, that's better. And this is going to be A31 divided by L11. Okay, yeah, and something was feeling not right. Okay, A11, let's just say we know is positive because the matrix A is positive definite. Okay. Then now we're going to take this next column. And so we're going to get A21. Let me see, we get L21 squared plus L22 squared has to equal A22. So that implies that L22 is going to take A22 minus L21 squared, which we already know, and take that to the 1/2 power, or the square root of that. Okay, and then L21 times L31 plus L22 times L32, and that has to equal A32. So that implies that L32 is equal to A32 minus L21 times L31 over L22. All right, and then the last one is L31 squared plus L22 squared plus L33 squared. And that has to equal A33. So that implies that L33 is going to take A33, going to subtract off L31 squared and L22 squared, and then raise that to the 1/2 power. Okay, so the full algorithm is in the text, all right, but in general, you have Lij is equal to aij minus the sum k equal 1 all the way up to j minus 1 of lik times ljk all over ljj. Okay, so this is I equal to 2 to n, and j equal 1 to n minus 1. And then you get LII turns out to be AII minus a sum, k equal 1 all the way up to I minus 1 of LIK squared. All right, so that's how we deal with that. All right, so we've looked at the Koleski method. First, we looked at Gauss-Jordan method, and then we looked at the Koleski method. And so now here's the Koleski, more of the Koleski method and the algorithm. So that's how we solve that. Okay, so next we want to look at tri-diagonal systems. Okay. So the matrix A equal to Aij is tri-diagonal if Aij is equal to 0 for the absolute value of I minus j bigger than 1. Okay. So this is a matrix A that looks like A1, 1, A1, 2, A2, 1, A2, 2, A2, 3, A3, 2, A3, 3, A3, 4, and it goes all the way down to AN minus 1, N, AN, N minus 1, ANN. Everything out here is 0. Everything out here is 0. Okay. Now, tri-diagonal matrices occur in a variety of applications. So the main one being boundary value problems. Okay. And it's also called the banded matrix of width 3. Okay, so there are other banded matrices. You can have pentadiagonal matrices. Okay, so this is easily factored into A is equal to LU. And it's done by doing L is a matrix that looks like L11, L21, L22, L31, L32, L33, dot, dot, dot. All the way down to L, N, N minus 1, L, N, N, target. Okay, and then U has ones on the diagonal. And then this is U12, U23, U34, U45, all the way down to U N minus 1N. Okay, so this is a really nice factorization. Again, easy to solve. Okay, all right, so we can take a 3x3 example, just like we did before. Okay, so A is equal to LU. So we have A11, A12, A13, A21, A22, A23, A31, A32, A33. That's going to equal L11, L21, L22, 0, L32, and L33, 0, 0, 0. And then this is going to be 1, 0, 0, U 2, 1, 1, U2, no, that's wrong. This is U12. This is U23, 0, 1, 0. Okay. So when we multiply this, you get L1 times 1. So A11 is L11. Okay. Okay, that's crazy. L11 is A11. Okay, then you get L21 is A21. Okay, then you get A12. You get A12 you get L11 times U12 is equal to A12. So now you know U12 is equal to A12 over L11. Then you get L21 times U12 plus L22, and that is equal to A22. So now that gives you that L22 is simply A22 minus L21, which we know, and U12, which we know. Okay, and then we get L32 is simply A32. And we get L22 times U23 is equal to A23. So now I can find U23 is A23 over L22. And then the last one is L32 times U23 plus L33 is equal to A33. So that gives us that L33 is equal to A33 minus L32 times U23. And this technique has a name. It's called the Kraft factorization algorithm. Okay, so this decomposes a tridiagonal A into LU. So at the first step, you have L11 is A11, and then U12 is equal to A12 divided by L11. Then you have to do I equal 2 to n minus 1, Lii, Lii minus 1 is equal to Ai, I minus 1, Lii becomes Aii minus Li, I minus 1 times Ui minus 1, I. And then you get U, I plus 1 is equal to Ai, I plus 1 divided by Lii. And then after you complete that, your last step is Ln n minus 1 turns out to be an, n minus 1, and then your last element, lnn. Come on, right up. Right up. There we go. lnn turns out to be ann minus ln n minus 1 times un minus 1 n. Okay, and it's actually a fun thing to code and see how it works out very nicely. Okay. After you do that, then you only have to solve a very simple algorithm to solve for ax equals b. So say you have ax equals b, and a is tridiagonal. Then we take LU, x is equal to b, and then you solve Ly is equal to b, where ux is equal to y. Okay, so you solve Ly is equal to b. So to do that, that would be step 4, and that would be yi would equal y1. Y1 would be b1 over L11. And then in step 5, you would have I equal 2 to n. You would have yi is going to be bi minus li, I minus 1, times yi minus 1. And all of that's divided by Lii. Okay. Then you solve ux equals y. And so that would just be x1 would be y1 minus u12 x2 x2. So obviously these are solved in the wrong order. You would get x3 would be y3. And then x2 would be y2 minus u23 times x3. And then x1 would be y1 minus u12 x2. Okay, and so how would you write that? That would be 6. That would be xn is yn, and then 7 would be I equal n minus 1 to 1 going backwards. So you would have xi would equal yi minus ui I plus 1 times xi plus 1. And there you go. So this algorithm only requires five n-4 operations. Crowd factorization is fast. So when you have a tri-diagonal matrix, you don't want to be doing all that other stuff to make it go on forever. In your program, you are going to use, you have to program Cholesky and decomposition and the LDL transpose decomposition to find the determinant of the matrix. So let's talk a little bit about determinants. I'm not going to say a whole lot about determinants. Okay. So we know how to compute determinants of a matrix. We also know from before theorem that A is non-singular. If and only if the determinant of A is not equal to 0. Okay, so at this stage, you're graduate students, so I know you know how to compute the determinant of a matrix. It is also true that the determinant of AB is equal to the determinant of A times the determinant of B. So from that, we can get that the determinant of A times A inverse is the determinant of A times the determinant of A inverse. But that is the determinant. I don't know why that did that to myself. I knew I didn't have enough space. The determinant. Okay, give it a minute. It's fighting with Zoom. Usually if I click something else, it comes back. Nope, still fighting with Zoom. Okay, now it's back. So the determinant of the identity matrix, we know that's 1. And that's the determinant of a matrix A times the determinant of A times A inverse. But that's the determinant of the matrix A times the determinant of the matrix A inverse. And so that implies that the determinant of A inverse is 1 over the determinant of A. Okay, so the reason why that's important is because if A is symmetric, positive, definite, you get the D, then A can equal to LDL transpose. So that implies then the determinant of the matrix A is equal to the determinant of LDL transpose. So that's equal to the determinant of L, determinant of D, and the determinant of L transpose. Now, why is that so important? Why is that easy now to do? What do you know about the determinant of a lower triangular matrix? What do you know about the determinant of a lower triangular matrix? Or an upper triangular matrix? Are both of y'all on here? So if A is upper triangular, lower triangular, or diagonal, then the determinant of A is just the product of its diagonal entries. So therefore, the determinant of A is going to be L11, L22, all the way down to LNN. And then it's going to be D11, D22, all the way down to DNN. And then L11 again, L22, all the way down to LNN. So you can compute the determinant of the matrix if you can find that LDL transpose. So the determinant of A becomes L11 squared, L22 squared, all the way down to LNN squared times D11, D22, DNN. So you'll need to put that in your code in order to compute that. Okay. Let's talk about the matrix norms and condition numbers. Okay. All right. So let's take a single vector in Rn. Okay. All right. So then we can talk about the Euclidean norm. All right. Which is written to is just the sum I equals 1 to n of the absolute value of x I squared, all raised to the 1/2 power. Okay, so we're used to seeing this. X1 squared plus x2 squared plus Okay. All right, so in general, there are other norms. We have the P norm. That's the sum. I equals 1 to n, the absolute value of xi to the p to the 1 over p power. Okay. And here, 1 is less than or equal to p, goes up to infinity. So the infinity norm and the 1 norm are as follows. The 1 norm just basically says sum them all up. Just sum up the absolute values of all the xi's. So that's the 1 norm, and the infinity norm says take the max of 1 less than or equal to I all the way up to n of the absolute value of xi. Okay, so generally these norms are usually around the same magnitude. So let's say x -2, 3, 6. So then the Euclidean norm squared is 4 plus 9 plus 36. So that's 49. So that means the Euclidean norm of x turns out to be 7. Okay. The 1 norm turns out to be 2 plus 3 plus 6. That turns out to be 11, even though that doesn't look like it. Okay. And then the infinity norm turns out to be 6. So they're all roughly the same magnitude. You don't see anything that looks like a 100. You know, it's not off by a power of 10. So that's what we have there. All right. So you've seen this before, but there's several rules about norms. So the first one is we want to represent, so we're going to let this represent the norm of a matrix A. So that is the norm of A times X. That thing is greater than or equal to 0. And the norm of A is actually equal to 0 if and only if A itself is the 0 matrix. 2, the norm of a K times a matrix A is the absolute value of K times the norm of A. Okay. 3, the norm of A plus B is less than or equal to the norm of A plus the norm of B. It's the triangular inequality. And the norm of A times B is also less than or equal to the norm of A times the norm of B. Now, what kind of norms do we have on the matrix A? Okay, well, the matrix A also has several norms. Okay, so the first one is the Frobenius norm. And that one is the norm of A with a little f down here. And that is equal to the double sum, I equal 1 to n, sum of j equal 1 to n. So we're adding up all the absolute values. Well, we're just squaring each of the entries, adding them up, and then taking the whole thing to the 1/2 power. Okay, so that's equivalent to our Euclidean norm for vector. Then what we have called the one norm. And this is the max of the column sum. So this is the max of 1 less than or equal to j less than or equal to n of the sum I equal 1 to n of the absolute value of aij. And then the infinity norm of A is the max of the row sum. So that's the max 1 less than or equal to I less than or equal to n of the sum j equals 1 to n of the absolute value of aij. Now I'm going to tell you, trying to remember all these things is crazy. The way I remember that the one norm is the max of the column sums. Is because the columns are vertical and so is a 1. The way I remember this is the max of the row sums is because rows are horizontal and so is infinity. Okay. So we have matrix A. I'll do a short one because I don't have time to do a big one. A equals 2, 3, minus 1, 4. Okay, so then the Frobenius norm of A squared is 4 plus 9 plus 1 plus 16. Is that right? 4 plus 9 plus 1 plus 16, that's 30. So therefore the Frobenius norm of A is the square root of 30. The one norm of A is the max of, so the column sum for the first one is 4 plus 1. And then for the second one, this is 4 plus 1, the max of 4 plus 1 and 3 plus 4. That equals 7. And the infinity norm, oh, why is that on the inside? That should be on the outside. Is the max of 2 plus 3 and 1 plus 4. That equals 5. And just for our own reference, the square root of 30 is approximately 5.48. So as you can see again, no norm is giving me 520 something. What did I say, 5.48? They're not the same, but be concerned about the magnitude of the norm. Okay, so that's the most important thing in trying to figure this out. Oh, I didn't talk about the spectral norm. Which one is that? Oh, the spectral norm is the largest eigenvalue. So yes, there's one more norm I forgot to define. Sorry. So, now where did y'all come from? How did all of that mess up? That's weird. Okay, so this one was the Frobenius norm squared. This one was the one norm, and this one was the infinity norm, and this was an example. If A is n by n, then the spectral norm which is written as A with the 2. All right, so that is the largest eigenvalue of A transpose A. Okay. All right. So MATLAB can do these.
Excuse me.
Yes.
The that's of norm of A square.
Which one?
The F. How did you do it?
You're talking about right here?
Yes.
Okay. So I took 2 squared, got 4, plus 3 squared, plus 1 squared, plus 4 squared.
Okay. Okay.
Yeah. So you take this. So the the Frobenius norm says square every term and add them all up, and then take the square root at the end.
Okay.
Okay.
All right.
All right. So now MATLAB. You can do this. So, you know, MATLAB has a lot of wonderful things. If you do with linear algebra, then you turn on all the linear algebra possibilities. So you can do things like reduced row, echelon form. So reduced row echelon form, is it just reduce? Oh, wait a minute. I'm thinking of something else. Let me be careful. I'm thinking of maple. I'm thinking of maple. So let's scratch that. Between having maple, MATLAB, and Java all in my head, and Fortran in my head at the same time, I have to be careful on what I'm saying. Okay, so we're going to take that back. But MATLAB can do the norm of A, and then you do FRO. And that gives you the Frobenius norm. You can do norm of A, INF. And that is the infinity norm. And then you can do the norm of A, 1, and that is the 1 norm. And then the norm of A with a 2 gives the spectral norm. Okay. All right, so let's talk about the condition number of a matrix. All right, so one of the things that I ran into some issues with my graduate student is the matrix that he was trying to invert was nearly singular. And a way to kind of determine whether or not a matrix is nearly singular or not is not just to do the determinant, because the determinant will give you a very small number, but to look at the condition number. Okay, so we did 1, 2, 3. So the condition number okay, and so in MATLAB, you can do the condition number of a matrix A, okay? Now, the larger the condition number, the more difficult it will be to invert the matrix A. So something that has a condition number of 1 is beautiful, okay? So let's look at AX equals B. So we define the condition number to be the determinant, no, the condition number of a matrix A is equal to the norm of A inverse times the norm of A. Okay, so that's the condition number. All right, so let's look at the facts. So let's say we want to solve AX equals B. Okay, and then X star is the computed solution. That's what you get. So now AX star is not necessarily going to give you B, but it's going to give you B plus some error. So now we're going to subtract AX star minus AX. So AX star minus AX is going to give me B plus R minus B. Okay. So now I have A times X star minus X is equal to the residual. All right. So say A has an inverse, then I get X bar star minus X bar is A inverse times the residual. So now I want to take a norm. So the norm of X star minus X. So this is how far X is away from. That's the norm of the error vector. By the norms is less than or equal to the norm of A inverse times the norm of R. Okay. So I'm going to multiply the right-hand side by 1. So I'm going to get x star minus x is less than or equal to the norm of A inverse times the norm of R. And I'm going to multiply by the norm of B over the norm of B. So let's just multiply by 1. So now I'm going to get the norm of x star minus x is the norm. And now I'm going to get A inverse times length of the norm of B times over here, the length of R, the norm of R over the norm of B. Now, we just said AX equals B is what we're really trying to get. So therefore, in the place of B, and I should have some less than or equals here. So in the place of B, I'm going to put AX. So here we get x star minus x. So I'm going to get the length of A inverse times the length of A times the length of X times the length of R, or the norm of R over the norm of B. Okay. So now I'm going to divide both sides by X. And when I do that, I get this is the relative error in my solution. And that is less than or equal to this number, the length of A inverse, times the length of A, times the length of R, or the norm of R. Should not be saying a length over the norm of B. So length of A inverse. So this little guy right here is the condition number. This little guy over here is the relative error. Okay, in approximating x bar by x bar star. And then this guy over here is the residual error. Okay, so that's the relative residual. So the smaller the condition number in A, the better your solution to AX equals B. Okay, the bigger your condition number, the bigger your relative error can grow. So if the condition number of the matrix A is relatively 1, 10, 11, 9, we say A is well conditioned. And the system AX equals B is well conditioned. If the condition number of A is much, much bigger than 1, then A is ill conditioned. Now, MATLAB has a lot of tricks in it that it uses to be able to try to solve AX equals B when the matrix is somewhat ill-conditioned. Okay. Which time? I got 7 minutes. Okay, so here's an example. All right, so 3.9x plus x1 plus 1.6 x2 is equal to 55, and 6.8 x1 plus 2.9 x2 is equal to 9.7. So I want to solve this AX equals B. Okay, so the matrix A looks like 3.9, 1.6, 6.8, and 2.9. Nice 2x2 system. So it's easy to find A inverse, which is 6.7, 42, sorry, negative 3.7209, negative 15.8140, and 9.0698. So now if I take the infinity norm of A, I end up with the max of that is not right. Yes, it is. The max of 5.5 and 9.7. So that turns out to be 9.7. And the infinity norm of A inverse is the max of 10.5 and 24.9. And that's 24.9. So the condition number of A turns out to be 200, with the infinity norm. Okay, turns out to be 242. And that's bigger than 1. So the system is ill-conditioned. Now I'll tell you guys, that's nothing. My student Jose, the condition number of his matrix was like 2.67 times 10 to the 21. So his was hideous, but we had to figure out a way to get around it. Okay. So computing, like I said, in MATLAB, I used to teach a section on how to compute the condition number. I actually will do that, estimating the condition number. I'll talk about that, finish that up on Thursday, because we only have 2 minutes. My goodness, my scroll. Okay, so estimating the condition number. So we can still estimate the condition number, even though in MATLAB we can find it directly. Okay, so computing A inverse and its norm is expensive. All right, and gives rise to error and may have round off errors. Okay, so if T-digit arithmetic is used, okay, during Gaussian elimination, all right, then you can take the absolute value of R is equal to 10 to the T, 10 to the negative T times the norm of A times X, so norm of X star. Okay, so we'll finish here, there, and then next week, we're going to do some stuff with eigenvalues and eigenvectors. Please, 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 please make sure you remember how to find, y'all are graduate students. Y'all know how to find the eigenvalues and eigenvectors and all that kind of stuff. So I'm just going to say something briefly about the definition of an eigenvalue and an eigenvector and talk a little bit about the power method, and then we are going to be done. So we'll be doing that next week. Okay, I gave you guys your last homework and your last program. I'm gonna give you a take-home final, and we'll wrap it up. Okay, any questions? All righty, I will see you guys on Friday, I'll see you guys on Monday, Tuesday, with the exception of if you come to office hours tomorrow.